Doctor, I think your mic is muted.
Oh, sorry
Yeah,
for that. Okay, now. Okay, thank you very much.
yeah,
Okay,
okay.
sorry.
It's fine.
Okay. So I think we can continue our class. Okay, let me. Okay, so but this class will not be very long time. Okay, I think maybe around 40 minutes and so on, because my main focus of this class is actually on the solution on how to solve the two examples in the slides. Okay, so I think we have already know about the four quadrants operations and how the limitation of the rectifier circuit limits, okay, the operation of the motors, okay, because for the motor can operate four quadrants, but due to the limitation of the SCR, because SCR only allow current to be in one direction, okay, from anode to cathode, so meaning that it can only operate at a quadrant where the current is positive, okay, which is a Q1 and Q4 only, while Q2 and Q3 the current are negative, so that's why for this SCR they cannot operate, okay, in Q2 and Q3. And same with the three phase, okay, you can also use a three phase rectifiers. So three phase rectifier also only Q1 and Q4 only, okay, because of the use of the SCR. And please be reminded that the inductor here is very large. We consider the inductor very, very large compared to the resistant. Okay, so meaning that the current is assumed to be a DC current. Okay, so that's why for the calculation of the current, so we are using this formula. Okay, and in steady state operation, so we consider the inductor here to be short circuited, okay, because we know that the voltage drop across the inductors is equals to L didt. Okay, so if in the steady state where there is current, the current is steady, no change, no step change of the current and so on, so this one will become zero. So that's why for the steady state, the inductor is short circuited. So we have only VA, EA or EG sometimes, and also RA only. And then from that, you can calculate your current armature. Okay, and the current armature is at the rotor side. And for this circuit here, which is a field circuit, you have the what called field current. This is only used for what? To generate flux, okay? And flux, that flux will generate the magnetic field inside the motors. Okay, so I think this one you should know. Okay, DC motor is bidirectional. The DC motor itself, the structure, the motor itself, the current can be positive and the current can be negative. So that is what we call bidirectional. Okay, so no problem in terms of reversing, meaning that the motor rotation is in reverse direction. So no problem. It can be positive and it can be a negative rotation. Okay, clockwise or anti-clockwise. Okay. So, but the rectifier is the unidirectional. So, because the SCR are unidirectional device, so that's why it limits the operation of the DC motor. Okay. However, if the rectifier is fully controlled, meaning that you are using SCR, it can be operated to become negative voltage. Okay. So you can have your VA, okay, the voltage terminal, to be positive or negative. Okay. So to be negative, so your alpha should be higher than or equals to 90 degrees. Okay. Because you know that for a single phase, okay, single phase rectifiers, the equation for the voltage terminal, which is the output of the rectifier, is 2 Vm over pi cos alpha. Okay. So if the alpha choose later than 90 degrees, so your Vt will become negative values. Okay. So when you have a Vt negative, meaning that your rotation will be also negative, meaning that the rotation is in the reverse direction. So that is what we call a reverse, okay? Okay, instead of using or controlling the alpha here, you can also make the rotation reverse by either using these by using the circuit. You modify the circuit. Okay, the first one is actually the armature reversal, meaning that you reverse, okay, the armature polarity by using contactors. The second one is by reverse the field terminals, okay? And the last one is a double converters. So let's see the example of the armature reversal using contactors. So this is actually the circuit, okay? So what is mean that your alpha is maintained, for example, 60 degrees, okay? You don't want to make your alpha greater than 90 degrees because of maybe some limitation and so on. So you want your alpha to be at 60 degrees. You know that when your alpha is 60 degrees, so your voltage terminal or your voltage output will be negative, will be positive, right? But how can we make that your VT become negative, but you maintain the alpha 60 degrees? Okay, so we are using contactors. Okay, so if you are using contactors 1, so meaning that it is actually so this one is actually positive terminals, and this one is your negative terminals, right? So it's actually equals to the polarity of your V out here. Okay, but when you change the contact from position 1 to position 2, okay, so this one will become negative and this one will become positive, because right now, as you can see, if you contact this one positive, this terminal will be connected to positive terminal of the motor, and this one will be connected to the negative terminal of the motor. Okay, so that's how we use. Okay, I hope you understand. Okay, so when, for example, if you have alpha 60 degrees, you want to maintain, okay, you don't want to increase your alpha to greater than 90 degrees, but you want your voltage terminal to be negative. So what you should do is just by using mechanical contactors. Okay, so you switch from position 1 to position 2, so that you can have your voltage output. The voltage across the motor here is negative. Okay, so that is for the first example. The second example we don't have, so I think we just ignore that. Okay, and then this is actually by using two rectifier circuits. Okay, so as you can see here, we have Q1 and Q4. This one is for these rectifiers, and for Q2 and Q3 is actually by these rectifiers. Okay, so Q1 and Q4 is actually when the current is positive. The current should be positive here, and the voltage can be either positive or negative by controlling for alpha here. So meaning that your alpha must be greater than 90 degrees, okay, to get negative. Okay, so IA is positive. Okay, IA is positive. Okay, and here we see that we actually flip the SCR circuit. So right now your current is like this. It seems that from the motor itself, from the view of the motor sees that the current is actually going out from the motor. So meaning that from the motor to the supply. So meaning that your current is negative, right? So your motor sees that the current is going out from the motor through to the supply, to the rectifier circuit. So it seems like it's actually a negative. So for these converters, so Q2 and Q3 will be operated by these converters. Okay, because the current is negative. So Q1 and Q4, the current is positive, and Q2 and Q3, the current is negative. Okay, so the voltage terminal can be positive and negative by controlling the alpha. Okay, so V negative, alpha must be greater or equals to 90 degrees. Okay, so by controlling the alpha here. So meaning that by using two rectifier circuit, we can operate your motor in all quadrant. . 。 . 。 。 . 。 . 。 . 。 . 。 . 。 . 。 . 。 . 。 . 。 . 。 。 . 。 。 . 。 . 。 。 . 。 。 . 。 。 . 。 。 . 。 。 . 。 。 . 。 . 。 . 。 . 。 Okay, so let's see. Let's do some example here. So a separately excited DC motor has a constant torque load, 60 Newton meters. So the motor is driven by full wave rectifier converters connected to a 240 volt RMS AC supply. The field constant of the motor is given K multiplied with IF is equal to 2.5 and the armature resistance is 2 ohm. So calculate the triggering angle, which is the alpha, for the motor to operate at 200 RPM and assume the current is continuous. Okay. So right now, let's assume that so this is the torque versus speed. Okay. Torque versus speed. And I draw my load torque, which is the constant torque load, which is this one, meaning that it's actually independent of speed, meaning that it is a constant torque. Okay, so this is your torque load. The value is 60 Newton meter. Okay, and then this load is connected to the DC motor. Okay, so I use black color lah. So you have this top speed characteristic of your motor. Should be a straight line, okay? So this one is your motor. So this one should be no load speed. Okay, this one is your starting torque. Okay, this one your speed is 0, right? 0 RPM. So this one is RPM. Okay, so the intersection between load TL, load, and also your motor characteristic will give you the speed of the motors. So right now, the speed of the motor is 200 RPM. Okay. So the question is, calculate what is your alpha. Okay. So if I draw the circuit, so this one is connected to a 240 volt RMS, so single phase. So I maybe just draw like this. Okay. That is a controlled rectifiers where you have alpha here. And then we draw the model of the DC motor. So I think I just draw R only because this is we consider this one is a steady state operation. So the inductor is we can ignore. Okay, because it is short circuit. So this one is your V terminal. This is your RA, which is if the value is 2 ohm. Okay, and then this is your back EMF, which is EA. And there are current flow, which is you have IA. And you should have this one, RF. Okay, and then we can also ignore the the LF, okay, because in the steady state, so we can ignore that. Okay, but this one is okay. We can ignore this one because as mentioned before, the field circuit is actually just to produce flux. Okay, so in this example, so we can ignore the calculation inside here. So our main cost calculation is actually on the armature circuit. Okay, so right now, meaning that you should get to get the alpha. Okay, you should get the VT first. Okay, because we know that VT is, because this is a single phase, you should VM over pi cos alpha, right? So meaning that you need to calculate this first. So to calculate the VT, what you need to do is to use the KVL here. So from here, we know that VT is equals to IARA plus EA. Is it correct? Okay. So right now, we have a problem. We don't know the values of your IA. We also don't know the values of your back EMF. So actually, your back EMF here, which is the voltage, is proportional with the speed. So right now, we know the speed, but we don't know, we need to actually obtain something. Okay, so let's try to obtain RA is given. So RA is given, which is 2 ohm. So right now, can you obtain the IA first? How to obtain the current armature? You should get that from the equation of torque, which is torque is equals to K IF IA. Okay, so this is your torque motors, right? Torque motors, or sometimes also called torque D, torque developed by the motors. Okay, and we should know that the torque of the motor should equals to the torque of the load, right? Because the intersection here. So meaning that your torque motor is also 60 Newton meter. Okay. So from that, 60 Newton meter, and you have the KIF right now, K multiplied with IF, okay, is 2.5. So from that, you can get your IA. Okay, so your IA is 60 over 2.5, which is very large. Your current is 24 amperes. Okay, so right now we have solved this part. So IA is 24 and your resistor is 2. But how to obtain this one, the back EMF? How to obtain back EMF? Okay, so back EMF. What is the equation for the back EMF? You should memorize, okay? Your back EMF is K IF by the speed of the motor. Okay. So sometimes this one is KI. Okay. Sometimes this one KF. This one is KE. But usually KF and KE is same. Okay. So that's why we just use K. Okay. Meaning that it is same. So E is equal to KIF speed. But the usually for the voltage here, the speed here must be in radian. Must be in radian per second. Right now, you are being given the values in RPM. So RPM convert to radian per second. You need to actually RPM multiply with 2 pi over 60 seconds. Okay, because 1 minute has 60 seconds. One rotation is 2 pi, right? So rotation per minute in radian. So one rotation is 2 pi radian. 1 minute is 60 seconds. So you need to RPM multiply with 2 pi over 60 seconds. So the rotation is 200 multiply with 2 pi over 60. So you should get your speed is 20.9. Okay. So meaning that this one is 2.5 multiply with 20.9. So you should get your values of voltage induced. Okay. Voltage induced is 52.3 volts. So right now you have all the information. Okay. So this one 24 multiplied with 2. So 24 multiplied with 2 ohm plus 52.3. So your answer should be around 100.3 volts. And then you substitute 100.3 volt at this. So 100.3. Then you can get your alpha. So your alpha is cos inverse. So 100.3 multiplied with pi over 2. Okay, multiply with square root 2 because you need to convert RMS into Vmax. Make sure that your mode, your mode of calculator in degree form. Okay. Because if you set your mode of calculator in radian, then you got problem. So I got this one, cos inverse is equals to 0.464. Okay. So from here, I can get my angle alpha is 62.3 degrees. Okay, so please always use the rotation should be used radian per second. Okay, radian per second. So if you receive a question that given the speed is in RPM, so you need to convert into radian per second. Okay. Any question before we move to the second example? The second example is much tougher than the first example. So, okay. So if there is no question, then we can move to the second question. But I think first of all, I want to turn on my whiteboard first. So an example. So this one came from your previous final exam. So a rectifier DC motor is supplied by a three-phase full control SCR 240 volt RMS 50 Hz per phase. The field is supplied by a single phase. Okay, so the information here, the armature circuit is supplied, okay, by the three-phase, but the field circuit, okay, the field circuit is supplied by a single phase. Okay, is supplied by a single phase. And the field current is set as maximum as possible. Okay, this one is also one important parameters here. And DC motor has this characteristic, which is the armature resistance is 0.3. The RF is 175. And the motor constant, as you can see, is 1.5 V over A radian per second. And we assume that the inductance of the armature and field circuit is very large. So meaning that the current is DC. And it says that if the delay angle is 45 degrees and the current that draws or flow inside your armature circuit is 30 amps. So calculate the developed torque. So actually the developed torque is equals to your torque motors, okay? The motor the torque that actually developed by the motor. So usually the torque motor should be equals to your torque load lah. Okay. Okay. So right now let's switch to my whiteboard. Okay, much easier I think. So if I draw my circuit, three phase, okay? So usually we are using, for the supply, we are using a Y connection, okay? For supply, for the generator, always, usually it is in a Y connection. Okay, and then this is a control SCR. And then we can draw our motor model, which is RA is 0.3. So RA 0.3, and you have your back EMF, which is EA here. And this one is your voltage terminal. And there is a current flow, which is IA. Okay, IA. And this one is 240 volt RMS. So this one is also 240 volt RMS. So this one is 240 volt RMS. So this one is A, B, and C. So this is your neutral current, neutral point. Okay, but the field circuit is okay, RF. We consider this one is a steady state. So meaning that your inductor is a short circuit. Okay. So your RF is supplied by a single phase. Okay. Which is 240 volt also RMS. Okay. And there is a current flow, which is we call IF. And the RF is here 175 ohm. Okay. So right now, it gives this alpha A. So alpha A is actually referring to the alpha armature. So this one is 45 degrees. And this one is alpha F, should be alpha F, right? Because it used SCR. But right now, it didn't give any information what is the value of your alpha F. Directly, there is no direct information, but the information is there. How to determine your alpha F here? Which parameters or which sentence that shows about information for the alpha F? This one, okay? The current of the field circuit is set as maximum as possible. So meaning that the current of IF is the most maximum values. So the most maximum values meaning that your alpha delay angle is 0, right? Because we know that if you delay the angle, your voltage will be smaller, the current will be also smaller because your load is only resistor, right? Because so meaning that your voltage and current, voltage RF and the current IF is proportional. So if you reduce the voltage, you reducing the current. Okay. So how to ensure the voltage is maximum is by setting the delay angle 0. Okay. So there is no delay angle. because we know when you delay the angle, you will get smaller voltage. Okay, so if I can recall, okay, this one is when you have alpha is 0. Okay, you will have a full rectification. But if your for example, if your alpha is 30 degrees, so you have this kind of shape. Okay, which is, you can see there is no voltage output here. So this is your V average. Okay, your V average here over pi. So if compare this one, if alpha is 0, so your V average is this one, which is full. Okay, so meaning that your alpha F should be set equal to 0 so that the current is maximum. So that is the information, indirect information that you can extract from this sentence. Okay. Okay. Next is what? Oh, the current. The current armature is 30 amperes. So this one, the current is given 30 amperes. The RA is 0.3. And then it also gives you the K. So right now, we assume that your KT and also your KE is equals 1.5, okay? KT is for the torque and KE is for the back EMF. So we assume both are same. So calculate, okay, what next? The torque, So meaning the torque. The torque of their motor is KT IF IA. Okay. So KT is given 1.5. IA is also given 30 amperes. But right now, IF is not given. Okay, you need to calculate the IF. So we refer to this circuit, the phase circuit. So this is a single phase. So meaning that your voltage VF, okay, your voltage output of your rectifier, which is your VF, is 2 Vm over pi cos alpha. And since alpha is 0, so meaning that this is 1, right? So 2 multiplied with square root 2, because we want to convert RMS to Vmax, 240 over pi. So you should get your VF is equals to 678.8 volts. Okay, and since the right now the element here is only resistant, so meaning that your IF directly can get VF over RF. Okay, there is no inductor right here because we assume steady state condition, so the inductor is short circuited. So 678.8 over RF 175 ohm. So your IF is 3.878 amperes. So from that, you have already obtained your IF. So just substitute the value. Betul ke ni? Please check. 2 Vm. Is it 2 Vm? Because it's actually not same with the answer. The answer is 55.58. Ada salah ni. There is something wrong. So let's check VF. 2 multiply with square root 2 multiply with 240.
It's 216.
Okay, 216.
VF.
Yeah, 216. Sorry, yeah.
Yeah.
216. So 216. So this one should be over 175. So 1.23.
Yes.
So this one should be 1.23. So 1.5 multiplied with 1.23 multiplied with 30 amperes, you should get 55.35 Newton meter. Okay. So that is the torque developed by the motors due to the current of 30 amperes and the firing angle of the armature circuit, 45 degrees. Okay, so right now, the second question, the speed of the motors. Okay, so we already know the speed, the equation of the armature circuit is Vt is equals to IARA plus EA. Okay, so right now your Vt is actually from three-phase, right? You are using three-phase circuit, so meaning that the value is 3 multiplied with Vm line to line over pi cos alpha. Okay, so calculate. So 3 multiplied with, so right now, your Vm line to line. So if you refer to the connection of the supply, so this one is the Y connection. And for Y connection, V line is equals to square root 3 of V phase. Okay, please always remember that. V line is equals to square root 3 V phase. So right now, your V phase is 240 volt RMS. Okay. So you need to convert into V line. So square root 3. Okay. So that one is RMS. So you need to convert into Vm. So you need to multiply with square root 2. 240 volt RMS. Okay. Over pi cos alpha. Cos 45 degrees. So you should get your V terminal is 396.9 volt. Okay. So what is meant by that is actually this one. The VT here. The voltage output of the three-phase rectifier is 396.9. So, and then you substitute here. So, I can get my values 396.9. My IA is 30 amperes. Multiplied with my IR. R is actually 0.3 ohm. Plus EA. Okay. Because the speed, we can get the speed from this back EMF formula. Okay. So, from that, so this one T3 0.3. So 396.9 minus 9 volt. So this one is equals to EA. So your EA is 387.9. Okay. And we know that your EA is K IF speed, right? And your K, I think your K is given 1.5. Your IF is also given 1.2, if not mistaken. 1.23, yeah. So your speed in radian per second is 387.9 over 1.5 multiply 1.23. Okay, so 210.3 radian per second. Okay. Okay. Any question? So if there is no question, then we can move to the next last question. Okay, which is this one. If the polarity, mana saya nak pandang ni? If the polarity of the field current is reversed, okay. So like very challenging ni. What happen when you actually the polarity of the field current is reversed right now. The polarity of the is reversed. What is mean by that? So right now, your current that you have already calculated is 1.3 amperes. Okay. The question is, if the polarity of the field current is reversed, meaning that your IF is in negative direction. That is the information that we can extract from this information. If the polarity of the field current is reversed, so meaning that the current is right now is in negative values. Okay. So when it is reversed, automatically their EA will be negative, right? Because we know that Y is negative because we know that EA is KIF speed, right? So if IF is negative, so the voltage induced back EMF will be also negative. Okay. So for the same armature current of 30 amperes, okay, so meaning that your current armature is still maintain positive 30 amperes. Determine the required delay angle of the armature converters. Okay, so right now your IF is negative 1.23. So your voltage induced should be negative, and since the only change is actually the polarity, so meaning that the voltage induced is actually still same, right? Where is it? This one, 387.9. So this one will be negative 387.9 volt. Okay, negative. So from that, it asks you to calculate what is the new delay angle for that converters. So we know that still we are using VT is equals to IARA plus EA. Okay, so your IA is maintained 30. Your RA is also maintained, which is 0.3 ohm. And your EA right now is negative 387.9 volts. So this one will be 9 minus 387.9, and it will give you 378.9 volts. Okay. I think this one. Okay, so 387, and we know that your armature circuit is supplied by a three-phase. Okay, so meaning that your VT is 378.9 is equals to 3 multiplied with the VM line to line over pi cos alpha. Okay, so from that you can have 3 multiplied with square root 3, okay, multiply with square root 2, multiply with 240 volt RMS over pi, multiply with cos alpha. So from that you can get your alpha. Okay, so from here I can calculate 378.9 over 3, over 3 over square root 3 square root 2. Okay, so this one I got 47.5. Is it same with the answer? Oh, lain eh. Kena double check because the answer is actually not similar. 378, okay betul dah. 3M line to line, apa yang problem? Ada yang salah ni. 378, betul dah. Okay, please check eh. So I think I made maybe some ada salah. So what is your alpha here? Tidak betul dah ni. This one, okay. Oh, this one. Sorry. This one should be negative. Okay. Negative, okay. Negative 378.9. Okay, so this one should be negative. Okay, so this one should be negative. .378, okay, negative 378.9. 5, 3. Okay. 132. Okay, 132 degrees. Okay, betul lah tu. Okay. So my mistake is actually I forgot to put negative values. It should be negative, okay? So I think that's all. Any question that you didn't understand? Yes.
Yeah, doctor, I have a question.
Okay.
Excuse me, doctor, like what reference do you use for this chapter? What reference
Sorry?
should I use? What reference should we use for
Oh,
this?
reference. We don't have any reference.
Oh,
Sadly
I
to
see.
say, for this application of the DC motor using rectifiers, we don't have actually any proper reference.
So the questions the exam questions are normally like this one, right? Similar to this
Yeah,
one.
normally like this. Normally like this.
Okay, doctor. Thank you.
Mhm. Actually, for your information, usually students score very well in for the questions for the DC motor and AC motor. Okay, that is for your information lah.
Oh, okay. That's good. Thank you, doctor.
Okay, I think that's all from me. So I think maybe most of you are still in UTM. I don't know, still in UTM, or maybe some of you also have already gone to your hometown. So because your Hari Raya is actually in the corner. So maybe Monday or Tuesday, but I think probably Tuesday lah. Okay, probably Tuesday. Even though we have some history where our state in 1982, our state is actually have earlier Hari Raya, but I think if not mistaken, we as a region, the Asian region here, the Southern Asian region, they have standardized the dates. Okay, if Malaysia celebrate in Tuesday, so Indonesia, Brunei, and Singapore will also celebrate at the same day. Okay. Okay. So I think that's all from me, and meet you face to face, inshallah, after this semester break. Okay. And I think I would like to wish you Selamat Hari Raya, Maaf Zahir Batin. Okay. So for those who are driving home from UTM to your hometown, so drive carefully. Okay, kalau nak balik memang kena balik hari ni jugalah kot, because it will be a very heavy traffic jam, I think. I will go to my hometown, but not a village. It's a town which is Kuala Lumpur, because I'm from Kuala Lumpur, which is very near to KLCC. If I want to go to KLCC, only 10 minutes drive. So bukan budak kampung, so budak bandar. Okay, so I will back to my hometown on the 2nd of Raya. So I think tak ada jam sangat lah. Okay, so I think that's all from me. Thank you very much. Assalamualaikum.
Salam.
Selamat Raya.